Hello, everyone, and thank you for joining us today for our Quantum Speaker webinar series, hosted by ATARC's Global Quantum Working Group. I'm Lily Chen, one of the group's government co-chairs. We are very excited to welcome Alex Delgio and Sam Mercado to speak with us today. Alex and Sam are research scientists at the AWS Center for Quantum Computing in Pasadena, California. Alex's current research interests lie primarily in quantum algorithms and application, especially in the area of mathematical optimization. Sam's primary research interest is in quantum algorithms, with a particular focus on the quantum chemistry and simulation. In this talk, they will present examples and comment on takeaways identified in their larger survey of quantum algorithms and applications. There will be time for questions at the end of the presentation. Please feel free to utilize the Q&A feature and raise your hand at the end of the presentation. You will have an opportunity to speak. Now, we will have Alex and Sam to start. Welcome.
All right. Thank you. Thanks for the introduction, and thanks for having us here at the ATARC Speaker Series. As she mentioned, I'm Alex, and Sam will be taking over later in the talk. And we're here to talk about quantum algorithms, and in particular, a large survey document that we wrote together with a number of collaborators affiliated with the AWS Center for Quantum Computing. That goes over many different applications, and in particular end-to-end complexities, which is a concept I'll talk about in a few slides. So just as a roadmap for the talk, I'm going to say a few words about kind of the state of quantum algorithms and what we mean by end-to-end. And then Sam is going to give an overview of various applications and kind of resource estimates for these applications. And then we'll conclude with an outlook of what we've learned and open directions for the future. So I just wanted to say a few words to begin about kind of how we view the state of quantum algorithms at the moment. It's sort of a really nice time to be working on quantum algorithms. There's a lot of good things that have happened recently. And in fact, this year we're celebrating the 30th anniversary of the most famous quantum algorithm, which is Shor's algorithm for factoring numbers. Back when Shor discovered that algorithm in 1994, the field of quantum algorithms was very small and very niche. And since then, it's really grown into quite a large field. And as you might expect, we've discovered many things since then. We've really come to understand what makes quantum computers potentially very powerful. And we've developed a really large toolkit of what we call algorithmic primitives that allow us to design new quantum algorithms for new problems. In addition to this, there's been a lot of work, maybe in the last 10 years or so, on connecting what we know quantum computers are good at to actual problems that people in industry and science face that they would like to potentially solve with quantum computers. And then finally, the hardware has seen rapid improvements, and we can now sort of see on the horizon the advent of having fault-tolerant quantum computers that could be able to run some of these algorithms that have been discovered. But on the other hand, there are still several hurdles that we have to contend with. For one, as these quantum algorithms become more complex, we find that understanding them and kind of how they would be applied requires a lot of distinct domain expertise in many different areas that are hard to have all at once. Furthermore, while the hardware has made a lot of progress, there's still a huge gap between what we think will be needed to realize the best uses of quantum computers and what's currently available on the hardware. And then finally, and this might be a good thing in other contexts, but classical computers are getting better every year. which makes it harder for quantum computers to beat them. So this is sort of an issue when you're in our business of trying to provide advantages with quantum computers. But really, so at the AWS Center for Quantum Computing, where Sam and I work, and particularly on the quantum algorithms team, we really believe the present moment calls for us to really examine this gap between the theory, like what we know quantum computers are good at, and the practice. Like, how do we actually realize those applications, and how do we connect them to what users actually will want to use them for? And so this brings me to the this survey document that we wrote that's available on the archive, which doesn't propose any new quantum algorithms. It's sort of a survey of the literature, but it synthesizes a lot of these algorithms and kind of analyzes them with this end-to-end lens. And what we mean by that is what we want the analysis of the algorithm to really go from all the way from the input to the output. So the output of the problem should really be the thing that the user wanted to solve, not some other thing that might have been hard to obtain with the classical computer, but it's not actually so useful. And then furthermore, all of the costs of the algorithm should be carefully accounted for, including things that are often ignored, like the classical pre-processing and post-processing steps. There shouldn't be any caveats that are brushed under the rug. And finally, at the end of the day, when you have kind of a full estimate for how many resources the quantum computer will require, you should make sure to compare that to the best available alternative with classical methods to ensure a fair apples to apples comparison. And so this kind of thinking often leads us to work in this kind of flow chart depicted here. This is kind of how we imagine an end-to-end quantum algorithm and the analysis surrounding it. So at the one end, we would have a user application, and this might be something sort of vague, some goal that they want to achieve in their in their business, in their daily life or something. And the first step would be to translate this goal into a well-defined computational task. So some kind of input-output problem that if we knew the answer to, it would help us achieve that goal. And now this task could be run on a classical computer, or we could try to solve it on a classical computer, or we could try to solve it on a quantum computer. And we have to remember that we can't just throw a quantum computer at the problem and expect it to perform better than the classical computer. In fact, normally it would perform worse than the classical computer unless we are clever and we find a specific quantum algorithm that's able to solve that task. And that's where we come in, people who work on quantum algorithms. And luckily, the field has developed a very large toolkit of algorithmic primitives, so kind of subroutines that contain the essence of what makes quantum computing powerful. And we're able to kind of package these together into a higher level quantum algorithm that solves that computational task. But this isn't the end of the story, and that's because even if you've developed a quantum algorithm and you've shown that it can solve the task you're interested in, when you go to actually implement this on real hardware, we know that errors will occur in the hardware. So we have to go through an extra step, which is to compile that algorithm into a fault-tolerant implementation, usually by encoding the qubits of the algorithm into quantum error-correcting codes. This comes at the expense of using more qubits, so more physical qubits, and also more runtime than you would have thought if you had only been looking at the logical algorithm. But once we have this, we're ready to run this algorithm on actual hardware. Although, of course, this hardware isn't yet large enough or kind of noiseless enough to actually run this hardware, but we're trying to predict what will happen in the future. But if you're the user, then you would take this fault-tolerant implementation and you would run it on the hardware, and you would get an output that hopefully allows you to achieve your original goal. This process is also useful when we think about resource estimation, because it allows us to kind of isolate one of these levels of the stack and ask questions about how many resources would be required. So if we're thinking about the quantum algorithm itself, we'd be interested in counting, for example, the number of operations, the number of gates required by the algorithm, or the number of qubits it requires. When we go to implement it fault tolerantly, we'd be looking at how many physical qubits are required, or how many quantum error correcting code cycles are needed. And then finally, the user is probably most interested in quantities like how long will it take, or how many dollars will I have to spend to run this task on the quantum device. So this is the framework that we have when we think about quantum algorithms, and that we kind of adopted in this survey article. And before I pass it off to Sam, I just wanted to make one final comment about the article and its focus on fault-tolerant quantum algorithms over NISQ algorithms. So here, when we say NISQ, we mean noisy intermediate scale quantum devices, which are devices that can be fairly large, but don't have quantum error correction, and therefore can only perform a limited number of operations before the noise overwhelms the system. And the survey has not really focused too much on those algorithms, because we believe in the long term, these fault tolerant algorithms will be much more powerful. Also, we often it's hard to analyze these NISQ algorithms because they're more heuristic, and it's hard to come up with provable guarantees. But that's not to say it's not interesting to think about NISQ, and it's not something that we're dismissive of, just that it wasn't the emphasis of our survey. Okay, and I guess with that, I'll pass it off to Sam. Yeah.
Great. Thanks, Alex. Hopefully everyone can see my screen. Please tell me if you can't. So in the next section, I will be talking about what exactly is contained in the document, and giving a bit more motivation for why we selected the different content and ways of presenting it, and what you can do with the information in the document and how you can use it to solve problems that might come up in your own research. So we divided our document up into 3 key sections. And the idea of this was that it would mirror the different layers of the quantum computing stack. So at the top, you have different areas of application. So the domains where one might try and solve problems using quantum computers. This includes things like simulation of chemistry or particle physics problems, all the way through to finance or machine learning or optimization problems. We divided it up in this way because what may be of interest to one customer might not be of interest to another. The next layer down in the stack would be algorithmic primitives. So as Alex alluded to, these are common subroutines within the quantum algorithm practitioner's toolkit that can be used in a wide variety of applications and will come up again and again. So we really wanted this as a separate section so that users could see how often these different subroutines are applied, how they change within different applications, and really understand them as a standalone primitive. Then at the bottom layer of the stack, we have a section on fault-tolerant quantum computation and quantum error correction. The idea here is that, as Alex said, we're really considering algorithms that are going to need very deep circuits, and so are going to need to run with quantum error correction. And so we really need to understand how to translate these algorithms expressed in high-level quantum algorithmic primitives as raw operations that could be expressed on different quantum hardware platforms. And this should be able to tell us exactly how many qubits, physical qubits, we're going to need at the end of the day, and how long these algorithms are going to take to run. So first, I'm going to look in a bit more detail at the different areas of application. So you can see that we divided up into a number of areas. At a high level, we have things like simulation, logistics, machine learning, and cryptanalysis. Each of these sections, despite being broadly different on the face of it, we made sure to express using the same kind of template and layout for each of these applications. The idea of this and our motivation was that all of these different applications could then be compared on a roughly equal footing. So if you wanted to understand what applications might be best suited for running on future quantum computers, you can easily look between the different applications section and compare them without having to worry about all the nuances between the different areas. We also made sure to include the same kinds of information in each section, which includes the exact mathematical definition of the problem that we're trying to solve within these areas. And there may be a number of such problems. For example, in finance, we're interested in problems like pricing financial options, but also in things like optimizing financial portfolios. And these are solved in different ways. And so we have 2 different subsections within that section dealing with each of these problems. Once we've carefully defined the mathematical problem that we want to solve, we also carefully explain what the quantum algorithm is, taking into account all caveats, including things like loading data into the algorithm and reading it out at the end. This then allows for apples to apples comparison between best quantum algorithms that we know today for these problems and the best classical algorithms, which are also discussed in each of these sections. And this then allows users to go very quickly into the document and understand where we're at with quantum algorithms for a given application today, where the best classical computers are, and what we need to do to close the gap between them. So for people who are more interested in practicing and working on quantum algorithms, we have this substantial section on quantum algorithmic primitives. The primitives covered range from simple, well-known techniques that one can also find in quantum computing textbooks, things like quantum Fourier transform and quantum phase estimation, all the way through to very modern, state-of-the-art techniques. So quantum algorithms for Gibbs sampling, which have only been developed within the last couple of years, and also the whole quantum linear algebra toolkit, including block encodings and quantum singular value transformation, that have really revolutionized the field of quantum algorithms in the last few years. As with the application section, we use a uniform template between each of these primitive sections. The template is designed so that we really strip out a lot of the additional content that might be included in research papers describing these primitives originally, and instead you can cut straight through to what are the resource costs for these primitives in terms of the number of qubits and number of gates that you need. What exactly are they achieving, and what caveats are there that you need to be aware of when applying these primitives in different scenarios? And as we discussed, there's a lot of linking throughout this document, and within these primitives section, there are links to all the applications that might use them, so you can really see how these things get used in practice. Then, as the final layer of the stack, we have this section on fault-tolerant quantum computation and quantum error correction. We are primarily considering error correction within the surface code, as this is arguably the most well-studied quantum computing code and is very practical for a number of architectures, and so it's being considered as the front runner for many entities who are trying to build quantum computers. The aim of this section is that you can take the inputs from other parts of the document. So for example, you can look at a particular application and understand how many logical qubits were required and how many logical gates were needed to solve that problem. You can combine that with parameters that may be specialized to your particular hardware platform, like the physical clock speed or the error rates of your hardware. And then you can run them through a series of steps described in this section, which will convert these logical resource estimates into physical resource estimates, explaining the number of physical qubits you need and the runtime required to solve these algorithms on real quantum hardware available in the future. So this really makes this full then like end-to-end connection between quantum applications at a very high level, now trying to run these on real hardware at the machine level. So we can actually do these steps in practice, full end-to-end resource estimates with the information that's contained in the document. Unfortunately, we won't have time to go through all of these steps today in this short talk, but if you're interested, you can follow up on the blog link shown here, where Alex and I really step through each of these parts of the procedure carefully to understand what resources you might need for a particular problem. The problem we were focusing on is the Fermi-Hubbard model and simulating that. So the Fermi-Hubbard model is a simplified model of condensed matter systems, including high-temperature superconductors. And the document really contains all the information you need to understand the quantum computing costs of solving this problem. And classically, it's a hard problem to solve. So this is genuinely something that people care about. So the document itself, at the high-level quantum application section, has a whole section on the Fermi-Hubbard model explaining what this is, why we care about it, precisely defining the mathematical problem we want to solve, and then outlining what the high-level quantum algorithm for this problem is. You can then step through the document into the different primitive sections, so things like block encoding or quantum phase estimation, to understand what their costs would be for the particular case of the Fermi-Hubbard model. Then once you have these high-level resource estimates, you can plug these in to the section on fault-tolerant quantum computing and quantum error correction and translate the logical gate and qubit costs into physical costs for running on quantum hardware in the future. So this can be done not just for the Fermi-Hubbard model, but for a whole range of different models and problems that are described in the document. So shown here are some of the different resource estimates that have been performed either by us or are available in the literature and are tracked in the document for solving different problems on quantum computers. And you can see that, really different problems are more or less suited for running on quantum computers and maybe easier to run in the near future. So things that are very naturally quantum native, things like simulating other quantum systems, seems to run with very few quantum gates, and so is an attractive target for running on the first generations of error-corrected devices. On the other hand, problems that are primarily classical in nature, things like finance, may require a larger number of gates to achieve, and so we may have to wait longer to solve these kinds of problems. The elephant in the room here is really quantum machine learning. As well, there's been a lot of different work on proposing different quantum algorithms to solve machine learning problems. There haven't been many concrete resource estimates or any concrete resource estimates, to the best of our knowledge, performed yet, really comparing how quantum computers would perform for these really important problems to how the best state-of-the-art classical algorithms would perform. So writing this document has been, I think, really helpful for our team in terms of understanding the landscape of quantum applications and what kind of work is required to continue moving the field forwards. So probably the most important takeaway is for many of the algorithms that we have provable guarantees for, we need very deep circuits with billions of logical gates. And as a result, when we apply quantum error correction to make these problems feasible, we're going to require hundreds of thousands, if not millions, of physical qubits. Now, clearly, this is considerably more than we have available in state-of-the-art machines today. And this suggests that we're going to have to wait a number of years before we're able to solve the state-of-the-art problems that people really care about with quantum computers. So what can we do in the meantime? Well, between now and then, we can continue to optimize the hardware to try and bring these resources down and develop the large-scale machines that we're going to need. But as well, we can be working to better understand and develop the quantum algorithms. Work in recent years has shaved off huge factors from the runtimes and resources required for quantum algorithms. And we believe as we develop improved techniques, this will continue to be the case. In addition, we can search for new applications as well as optimizing existing applications, as it may be that we find things that are even better suited for quantum computers. In particular, this large step is really, I think, the last step is a key takeaway for what we would like to do with our research going forwards, and something that we'd like to further develop in our document. So there are a number of smaller improvements that we'd like to make to the document, to the field in general. For example, there are additional resource estimates that could be done more carefully for things like machine learning applications or additional topics in optimization, like solving semi-definite programs. There's also some caveats that have not been fully addressed within a lot of the quantum resource estimates. So for example, the Fermi-Hubbard case that I talked about before, we often think of just the resources to apply a certain step to the algorithm known as quantum phase estimation. But to run the algorithm in a fully end-to-end fashion, we also need a good starting state for the algorithm. And this part is often not costed out, and we don't necessarily know of a foolproof way to achieve that yet. So this is something that also needs to be included in future resource estimates. But definitely the most important step is to really develop this connection between the output of the quantum computer, what problem it actually solves for us, and the problem that we really want to solve, and that we're used to solving on classical computers. Because trying to join up these two ends of the pipeline and try and identify applications where quantum computers are a more natural fit will really reduce the resources we need and make classical computers have to work harder to compete. So that's all the content we have today. We've been conscious to try and leave a good few minutes for questions. And if we aren't able to address all questions at this time, then feel free to email us and follow up, and we'll try to answer your questions there. But thanks all very much for attending and for listening, and we're happy to answer questions now.
Thank you, Alex and Sam, for a great presentation. And I saw some questions already answered through Q&A. Any more questions? We have about 4 minutes for questions.
Yeah, I'll just jump on as well, because there are a couple of questions we saved until later. So I'll just repeat them here for Sam and Alex. So question from Howard Brown, which quantum resource estimation tool do you guys prefer and why? Or how do you approach that?
Yeah, I guess I would say, so personally, I haven't honestly used many of the tools out there. I know that there have been some released fairly recently, and I think it's an ongoing project to kind of improve the versatility of these tools. So I would like to use them more. Often our kind of work in this is a bit more kind of higher level and like pencil and paper, sometimes back of the envelope calculations. But it would be good to become more fine-grained and really get a more precise sense. So yeah, I don't really have a perfect answer to that question.
And a somewhat related question from our good friend Travis Shelton at IBM. He asks, how difficult would it be to redo your estimates using other codes beyond a surface code?
I think it wouldn't be too tricky. Our resource estimates that are contained in the document, or at least in the fault tolerance section, are not heavily optimized for runtime within the surface code. As Alex says, they're primarily designed to be a back of the envelope that captures the majority of the scaling cost. But if one had a good phenomenological model of given a set number of T gates, how you then run that within an alternative code, you could easily compute those resource estimates there.
Great. That's all the open questions on the docket right now. Unless anyone else has got a last minute one to put in. Oh, a couple just popped in. Travis says thank you. One from Conrad Hopt. In the slide with the example resource requirements for different applications, is the number of gates the depth of the quantum algorithm or circuit, or is it sort of the total number of instructions that need to be executed?
That's a good question. So in these kinds of resource estimates shown here, this will typically be the total number of logical gates required. And many quantum resource estimates imagine running these sequentially. In fact, technically, it's not even all of the logical gates. This is probably just the total number of logical T or Toffoli gates, like non-Clifford gates in general, because we often consider running these as much more costly than running Clifford gates would be. And a lot of work looking at running fault-tolerant quantum algorithms imagines running these gates sequentially, because it will incur a lot of additional resources to run them in parallel. So you can kind of think about it as the sequential depth of these algorithms as well.
That's great. There's another question from an anonymous attendee asking about the different quantum services that we use, whether Bracket or Qiskit or others. I'll take that one offline and type the answer to that because I do Bracket. But Celia Mosbacher from QEDC, hey Celia, asks, are there any areas of academic research that you'd like the Federal National Quantum Initiative to invest in?
Maybe we could take that one offline as well, because I feel like we probably do have some thoughts, but maybe it would be best to think about them and write them down carefully.
Sure.
Convey those that way.
Celia, let's arrange a direct phone call in the next week or so and catch up. Then Jordan Janone asks, what work is being done in QML resource estimation with HPC quantum acceleration? So is there a quantum classical hybrid resource estimation for quantum machine learning?
Yeah, I guess I would say I'm sure that this kind of stuff is being worked on. These hybrid algorithms, which are quite popular and can even be run on like existing NISQ hardware. But it was definitely not the focus of our survey and kind of our general research focus. So I'm not really sure what the current status is on like the best tools and often the issue with these is we don't know how they'll scale. Like you can do tests on small sizes, and then you kind of have to hope that the results will extrapolate to larger scales, and we're not quite sure about that.
Gotcha. And I think we're out of time. So Amy, do you want to wrap us up?
So thank you, everyone. I guess we like to wrap up here. Thank you for joining this seminar today.
Yeah, thank you for having us.
Yeah, thanks everyone for listening.
Thank you.